Student, welcome to our physics discussion, that is physics in a smart way. Here we are we do go into a topic that I think we have not touched before, that is heat and thermodynamics. That is heat and thermodynamics. So far as future of your studies are concerned, this is an important topic. Somebody wants to study anything related to thermal science, like mechanical engineering and all that, those are highly essential. Anything goes for pure physics study, that is also essential. And the topic is endowed with very high quality mathematics and is an interesting one. So basically, we go to heat and thermodynamics, and so far as entry is concerned, entry to this topic can be made at multiple points. And mind it, this heat and thermodynamics that includes kinetic theory, of gases that I shall be considering, that includes kinetic theory of gases, KT theory of gas. Okay, so thereby the entry to this topic can be done in many different ways. It just depends upon the things we are really interested in, and we can move on. So far as the heading portion and all those things is concerned, I am removing that because I need a lot of space. Here we make a progress that is big practical one, and we start with the idea. We start with the issue that is work, and here work means sorry, my pen malfunctions. Thermodynamic work. Thermodynamic work. So far as work we have gone through, in work, energy and power, in mechanics, usually work, to find out work, we use two formulas, work equal to F dot S, the dot product of force and displacement. Okay. The same work also sometimes we put it as integration of your FDS, integration of F dot ds, starting from S0, sorry, let me change the color, starting from S0 to S1, or starting from, if I remove all those 0 1 bombastic subtitles, starting from 0 to 1 or 1 to 2, we may say also, that is much better. 1 to 2, if the initial state is 1 and final state is 2, so we can put it like this. So these two formulas are usually the formula we use to find work, and this formula is very much valid or very much useful if our force is a constant force. If our force is a constant force. But the second formula, we got no choice but to take its help if the force is variable, because for a variable force, work at every instant, for every small displacement, force will be changing. So thereby, you have to take the help of with sophisticated mathematics. So if F is variable, F is not constant, then we got the second formula, that is work equal to integration of ds. Okay, these are two different styles. They mean the same thing, but the thing is that our usage or our situation is different. If the force is constant, then we take the formula that is F dot S. If the force is variable, then the formula is okay. But the thing is that those are the regular formula of work, we know work and all that. But now we are in thermodynamics. In thermodynamics, we don't go for finding the force, finding the displacement. they are not popular. Force is not so popular, but rather pressure is popular. So thereby we can change our style in a bit. If we are in thermodynamics, or we can say thermodynamically, work can be found out as your F dot S. We write that is F dot S. Or basically we may think as F into S, no problem, no harm, Mr. F equal to, that is pressure into area. I am immediately coming down to the scalar way, because your vector approach is not so important, so significant for me. Going for area vector and all those things, they are not so viable or should say helpful here. So force equal to pressure into area into displacement. We know if we are dealing with a sample of the gas molecules are there, they exert pressure, and on the piston, we have put some weight on the piston to counterbalance it. And if by chance the pressure increases and the piston goes for a displacement S, if our cylinder has got a base area A, I think you have gotten the idea. The cylinder has got base area A, and the gas inside it is with pressure P, an ideal gas, and due to some reason the gas expands and pushes out the piston, doesn't push out completely, pushes out the piston by a distance, that is S, by a distance S. So thereby we got no problem here with the force vector and all that. Force can be changed as pressure and area into, here we forgot the dot product, we say that is F into S. S means displacement. So when you multiply S with that displacement, we know that is equal to pressure is P into your area into displacement. When you multiply area into displacement, we know that is new volume created, extra volume created. Extra volume is delta V. So thereby we get the formula of work here, which is more suitable for thermodynamics, that is P into delta V. And vectors do not work in thermodynamics usually so well. We are coming down to scalar level. But we know this formula is correct if the pressure is constant, for a constant pressure process. If the pressure is constant, just like the basis of this formula was the first equation, W equal to F into S. But if somebody considered the second way, we got the work equal to, the same thing can be easily expressed by looking at the formula. Work will be equal to integration of P dV, elemental volume starting from 1 to 2 or 0 to 1, if our pressure is not constant, or if the pressure is variable. So obviously P delta V is the favorite formula of the work for our constant pressure process. But there are many processes where pressure is not constant. So thereby the formula is to be, that is P delta. Apart from that, one thing we have missed here, when we say that is integration of PdV, integration means summation. So here our basic policy was, when we did try to find the work, we have added very small works, dW1 plus dW2 plus dW3 plus dW4, okay, dW3 plus dW4, like that, okay, and every dW will be coming with a formula, not dP, but P with a small displacement. If during the movement of hours, the pressure of the gas is changing in a regular way or in an irregular way, then we divide the displacement into small displacements, ds, 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 like that. And for a particular pressure, if you make PdS, then that gives us that is into your area, So that gives us PDV, and PDV is the small work. So whenever you are involved with some intricate mathematics in thermodynamics, if it's a constant pressure process, then it is P delta V work formula, or it is integration PDV. But integration PDV usually starts with the idea the dW, or a very small work, is always equal to is always equal to, let me remove, PDV. So these three formulas are, this is universally correct. This is correct only for a constant pressure process. This is also universally correct. So these three formulas of the general work. Apart from that, there is another way to find the work or to deal with the work, that is using the graph. A lot of graphs are supplied in thermodynamics using the help of graphs. But okay, that will be for a later date, not today. We will be considering that for our next lecture or next class. So thank you.